So we will spend about half the lecture on this, and then we'll move on to the basics of rotation today. So HC Verma was done, no doubts, Mini? Okay. Students, if you have any doubts in HC Verma, please send me the question numbers on text, then I can. Students who are attending offline, please send on. Yeah, any questions from HC Verma? Like I said, which one? This fourth one? Short answer type, okay. So this question says center of mass is defined by this, which we know, 1 upon m summation mr. Suppose we define center of mass by some other formula where q is charged like this and I is okay. Then can the center of charge of a two particle system lie outside the line joining the two charges? Okay, so now we are saying that instead of center of mass, we are defining something called center of charge. Okay. So let's say that is RC. Okay. And that center of charge is defined by 1 upon capital Q, which is total charge, into summation QI, not MI. QI RI like this. Okay. So this you can see is exactly like the formula for center of mass, which is okay, you're just replacing a little bit of time to get used to this. Okay. So you're just replacing mass with charge. Okay, so like this is the weighted mean position of mass. This is the weighted mean position of charge. Okay. So now, for example, the first thing is saying that can the center of charge of the two charge system be outside of the line segment joining the two charges? The answer is no, no. Because just like if you have two masses here, if you have a two particle system of mass m1 and m2, then the center of mass of that two particle system has to lie somewhere on that line joining the two of them. The center of mass has to lie over here. So like that, if we have a two charge system also, then the center of charge has to lie like this. It has to lie, let's say, like this. Okay, so that answers that part. Okay. Now, similarly, second part, if all the charges of the system are in the xy plane, is it necessary the center of mass will also yes, again the answer is that. Okay, so that part is also yes. If all the charges of a system lie in a cube, is it necessary that the charge of the center of charge will be in the cube? Okay, now the only thing that we have to consider over here, something which is important, is that charge is what kind of quantity? It can have plus minus sign, whereas mass is what kind of quantity? It could have only so now let's come back to this and let's see, can this go outside? Okay, let's answer the question like this. Like, let's say that this is our x-axis over here. Okay, this is the origin. Okay, now take the case where Q1 is, let's say, minus 10 microcoulombs and Q2 is plus 20 microcoulombs. Okay, and X1 is, let us say, 2 centimeters and X2 is, let us say, 4 centimeters. In fact, let's do it the other way. Let's make this one minus 40. Now see where the center of mass is going. Center of charge is going according to the formula. It's Q1 X1 plus Q2 X2 divided by Q1. So 80 is going to 0 now. So here, where is the center of charge? It's coming. So center of charge is here. It's not here anymore. Okay. So because the difference is that thing, the difference is in the algebraic nature. Okay. So that's why now that same logic, when you extend to 2 and 3 dimensions, you will see that it can lie outside the square also. It can lie outside the cube also for that reason. Because charge can be positive and negative. And here we are assuming that in this formula, charge is substituted with algebraic sign. But in case of mass, it is not substituted with. I mean, mass does not have sign. It's a magnitude quantity. Okay. All right. So that is clear, I hope. Next. Anyone else? Okay, let me check in the messages also here. If any of you have questions from HCV, let's finish that off first, people. So I have not received any text message from anyone. So I'm assuming that HCV is completed. What about you people? Anyone? Yeah. Which one? 60th. Okay, let's come to 60th question. Okay, so block is placed on a triangular block, which in turn is placed on a horizontal surface. Yeah. Find the velocity of the triangular block when the smaller block reaches the bottom end. Yeah. So this is a very interesting question where we have to apply a combination of concepts. See, all surfaces are frictionless. So energy will be conserved. Mechanical energy will be conserved. So the loss of gravitational potential energy will be the gain in kinetic energy of both the objects put together. But apart from that, what else can we conserve? Can we conserve momentum? How? Tell me. Only the horizontal momentum will be conserved, not overall momentum, but only the horizontal. So this is HC Verma, the main exercise. Question number 60. Everybody's benefit. Okay. So in this, what is happening? We have this kind of triangular wedge, which is of mass capital M, right? Okay. And this angle is given to us as alpha or whatever. So this is on a frictionless surface. And we release a particle or a small block or whatever of mass small m from here. This is at a height of h. Now we have to find the velocity of the wedge, the triangular wedge, at the instant when the particle just about reaches the is reaching the bottom end over there. Okay. So if you look at the interactive forces between them as the sliding is happening, as they are in the process of sliding. So now you can see that this is applying some kind of a normal reaction. This is applying an equal and opposite normal reaction. Okay. And then the other forces are all the external forces, which I'll show with a different color. So small mg, capital Mg, and some normal reaction with the ground is applying this. So as a result of that, this is moving with a relative velocity like this. In the ground frame, its velocity is actually different. Whereas this is moving with a velocity, let's say, which is v1 like this. So the actual velocity of the particle v2 will be the vector sum of that v1 plus v relative, which I have shown in the diagram. No, because this is the actual velocity. No? So this is the velocity of the particle in the ground frame. So this will be equal to the velocity of the wedge, okay, plus the velocity of the particle with respect to the wedge. What is it? Relative velocity is difference. No? So this is sum. Right now. Suppose I am running at a speed of 2 on a platform which is moving under me at a speed of 1. Then in ground frame, my velocity will become what? 3. No? It will not become 1. So that's vector sum. No? Yeah, see, it's a vector summation that I'm done. So sign will take care of itself. That too, this is not horizontal. This is not vertical. No, this is a vector sum relation that we have. Okay, so this is what we have to understand. Understanding this point, this V relative is the velocity of the particle with respect to the wedge. So the velocity of the particle in the ground frame will become the vector sum of this V1 and that V relative. Okay, so that's something we'll have to take into account. But before that, now you can see that in this system, what are the external forces? Mg and N0, and they are all vertical. So there is no horizontal external force, which means that the center of mass does not have any horizontal motion. But the center of mass does have vertical motion. So what is happening is, as this particle is coming down, this wedge is moving like this, the center of mass is actually coming down vertically. It's not that the center of mass is not moving, but it is moving only vertically. Okay. So if the center of mass right now is somewhere here, because the block's center of mass is here and the particle is here, then after some time the center of mass would have come down while this would have happened. Okay. So now we have to investigate for an instant when something like this is happening. Okay. So by then, let's say the wedge has gone here and the particle has come here. Okay. But the center of mass has only come down vertically. So by now, let's say the particle's relative velocity has become VR. Okay. So this is the particle's velocity relative to the wedge. Okay. Whereas the wedge's velocity is V1 at this instant. Okay. So what all will apply? We'll apply conservation of horizontal momentum only, not conservation of momentum. Okay. To this system. Okay. So that equation will give me what? That capital MV1 on this side has to be balanced by the horizontal component of that velocity. Can you tell me directly how much will be particle M1's horizontal velocity? No, VR cos alpha minus V1. Understanding? Because the particle's net velocity is the vector sum of this VR and V1. No? So the particle's net velocity is like this. It is the vector sum of VR and V1. Okay. So we look at the horizontal component. Okay. It is the vector sum of these two. So it is VR cos alpha minus V1. That is the particle's velocity in the ground frame. The particle's velocity in the ground frame from that relation, vector sum, is becoming VR cos alpha minus V1, okay, I cap plus V1, sorry, minus V1 sine alpha. This will also be required later for the energy conservation. That's why I'm writing it down below here. This is the particle's velocity in the ground frame. So when I'm doing horizontal momentum conservation, I'll put this over here. So the backward horizontal momentum of the wedge has to cancel the forward horizontal momentum of the oh sorry, VR minus VR. That's VR sign. Okay. So this has to be balanced by what? That momentum of the particle. So that momentum of the particle is how much? It is m into VR cos alpha minus V1. So that becomes our first equation. This becomes our first equation. Okay. And the second equation will come from conservation of energy. Right. So anything is given to us numerically? No, now we have to get everything parametrically. Okay. So and we have to get only V2 now.
So why can't we just work for what try to theta instead of alpha?
That's okay.
Turning around on
Yeah, because okay. So is the conservation equation clear to all of you? This one. Okay. Siddharth, you are also following this up to now. Same question you have also asked now. Okay, good. Okay. So for us, V1 and VR are unknowns. Okay, so we need the second equation. That's where our energy conservation will come in. Okay. So this equation, basically, I'm implementing this one. I'm implementing this concept over here. Where the stylus could have disappeared. Okay. Right. So let's move on to the next equation. So conservation of mechanical energy. Okay. So that will give us the relation that half m velocity of the particle square plus half capital M velocity of this one in ground frame squared. This is equal to mgh. And v1 is what we have to find out. Okay. So now remember, what is the velocity of the particle? Velocity of the particle was v relative cos alpha minus v1 I cap plus v relative sin alpha j cap. And we already had relation from equation 1. We have this thing that v relative cos alpha minus v1 is equal to capital M by small m into v1. Is this correct? Right. So if we substitute this information here, this gives us a very easy way to understand, okay, that v of the particle will become, this whole component can be replaced with m by m v1, because v1 is what we are trying to solve. But in the second component, we have to eliminate vr, because so how we'll eliminate v relative? That will become, now from here you can see v relative is this plus v1 upon cos alpha. Okay, so this plus v1 is how much? It is m by m plus 1 into v1 by cos alpha. Okay, so this is our v relative into sin alpha. Okay. See from here, see now directly what is VR? It is m by m plus 1 v1 divided by cos alpha. So I just replace VR with this thing, that into sin alpha. Okay. So what is the magnitude of this VP? It is v1 into square root of m by m whole square from this term. Okay, and then m by m plus 1 tan alpha, taking this and this together, whole square, this kind of term. Okay, so that's all we have to substitute here. It should be minus. This should be minus. Okay. The y component is negative. That's correct. Okay. Though I mean, will not make a difference to the magnitude, but yes, technically it is negative because we have taken y-axis upwards. Okay, but still that gives, okay. So now you can see that when I substitute these here, it's a very simple relation actually. V1 in terms of h is still very simple. So there are a lot of terms, sin alpha and all that, but it's not like you have to solve a quadratic equation or anything, because V1 square will be common everywhere. So next step, we'll substitute this here. So we can take V1 square common. Okay. So here we will get m into this term. Okay. Now we'll realize that when we take small m into this term, actually, you can take m square common from the denominator and outside and cancel it with this small m. So you will ultimately get what kind of a term? You will get some term which will look like this. It will be, oops. So we'll get a term which will have, now remember we are squaring this thing. Oh, so there's m square. That's okay. So there'll be, I'll have to divide by m finally. So there'll be this term. Okay. And capital M square plus capital M plus small m whole square tan square alpha. Okay. And the second term is half capital M V1 square. So finally we just take V1 square is equal to mgh. So from this we just have to find V1. Okay. So I don't know how the answer is given, whether it's some further simplification or something like this. Which one? No, because see, we are squaring this term. No? So when we square, we have m square in the denominator. Hey, see here VP square hai na? When we square, the square root goes away. So the LCM here is m square, and then there's half m outside. Okay. I mean, just when you do it on pen and paper, you will find it will work out. Okay. And then I think what they've done in HC Verma is they've taken this tan square alpha as sine square by cos square, taken LCM over here and transferred. So that's why they have that kind of ugly term. Anyway, so in a JEE question, you will get this with some numerical values and all. Sorry? You will get these with values of small m, capital M, and alpha adjusted in such a way that when you write these equations numerically, the first and second equation numerically, it will be easy to work out the final value. Okay. So, any doubt with this, anyone? Among students online also? Okay. So, let's take this further. Anything else remaining in HCV? Which one? 62. Okay. Let's discuss 62. Super dense material, no? Okay, so here what you have to do is you have to treat the earth. Okay. Oh. Like us, I mean, it's half the mass of the earth. No? Achha, you will basically need the formula of gravitational potential energy. Okay. So that only, no? Okay, let's understand this. So I'm moving forward from this now. So question 62. We will conserve energy. Okay, but the thing is now we cannot ignore the motion of the earth. Even though the size of the earth is much larger, but the mass of the earth is just twice of that. No? So when I release a particle, but of mass small m, which compared to the mass of the earth is just half the mass of the earth. So when I release it from a height h, where they will collide? They will not collide such that the earth remains there and the particle comes to a distance h. They'll collide at a position where such that the displacement of the particle will be 2/3 the displacement of the earth. So the earth would have literally gone up towards the particle by a distance of 1/3 of h, and the particle would have come down by a distance of 2/3 of h. So by the time they collide, so here right now if the distance between them is h, okay, so by the time they collide, something like this would have happened. Okay, so the particle and the earth would be like this, just like this, but the particle would have displaced by 2h by 3 downwards. Okay. And the earth would have gone up by h by 3. So their relative displacement, that is h. Okay, so they've collided. Okay. Now when they're about to collide, let's say the particle is having a velocity v1 and the earth is having a velocity v2. Okay, so such that again you can see that v1 is to v2 ratio will also be m2 is to m1, which here is 2 is to 1 because the mass of the earth is double of it. Okay, and the total kinetic energy of the system is equal to the loss in potential energy. So I don't know what they've asked in the question. Oh, when it's reduced to h by 2, so replace h with h by 2. Okay, so the potential energy is reduced by mg h by 2, small mg h by 2. So the kinetic energy has increased by that much. But take that the earth has a speed of v1 and the particle has, or rather particle has a speed of v1, the earth has a speed of v2. So there's m1 v1 equal to m2 v2. So let's do this like more schematically. Okay. So what is happening is, let's say initially this is h, okay, and now what is happening after some time, the earth has gone up a certain distance, the particle has come down a certain distance, so that the distance between them is reduced to h by 2. Okay, so by now the particle has a speed v1 and the earth has a speed v2. So that's it. Now we have to just apply the conservation principles. Okay. So v1 is to v2 will become 2 is to 1, because mass of the earth is to mass of the particle is 2 is to 1. Okay, and the sum of the kinetic energies is equal to the loss in potential energy. That's it. Okay, so now just in this replace me with 2m and replace that ratio of v1 v2, so you'll get the speed. Okay. Okay, anything else? 64th question, I think you would have found quite simple, direct formula based. Once you know that theorem that we discussed, perfectly elastic collision, equal masses, they always 90-degree divergence they have. Which one? Sorry, which one? Oh, this one. Huh?
I tried it again at home, but I couldn't.
Okay, now this is like a lengthy question, so let's do it properly today. Let's do it with the numerical values. Okay, then. Did anybody solve this question 38? So did you get a pattern or did you solve it like one by one you have to solve? There was no series that was being formed. Okay. Yeah, I also think there will not be a pattern that will be formed. We will have to solve it one after the other. But I think within 3 or 4 collisions, five collisions. So the fifth time I think B throws it, or the fifth time A throws it to B, his velocity becomes more than. Okay. Okay. If we, yes, it will be, because there is no pattern being followed. No? So definitely each collision, each event you have to solve numerically. It will be easier that way. I think you tried it parametrically, right? Then you gave up, because there's no pattern being formed. So try it numerically. I think you'll be able to do. You understood the process, yeah? Method kya use karna you understood. Okay. Achha, now let's come to module then. Any doubts on the module? Anyone?
Opposite does the answer this no.
Opposite as in?
I'm getting 3 by 2, they want 2 by 3.
3 by 2 कैसे हो सकता है बेटा? Because see, first of all, this is h by 2, no? So here what we are getting v1 square plus 2v1 square, 2v2 square is equal to gh. Okay. So that's why, no? No. Potential energy formula will be that only, no? Because h is very small compared to r. Potential energy only depends on the distance. Actually, it depends on the distance between the Earth's center and that body's center. So that has changed by h by 2. So the potential energy will reduce by mgh by 2. Okay, let me do one thing. Let me explain. See, to understand that now, see what I have done here, I have blindly used the formula. No, that with respect to the surface of the Earth, the particle has come down by h by 2. So how much potential energy has been lost? mgh by 2. But where this formula has come from and how I can apply it blindly, let's understand that over here. So here I am just using that blind formula, that delta U for gravitational potential energy of any particle of any mass. The mass doesn't matter, but it should be equal to mg delta y. But there is a boundation on this, no? So long as delta y is very small compared to the radius of the Earth. Why is this boundation there? Let's understand that. Okay. So for that, you have to delve a little deeper into gravitation, which we'll be doing very soon when we come to the chapter of gravitation. But there is a more interesting concept, because what happens is when you consider a huge spherical mass like the Earth, okay, and when you consider a particle of mass m, okay, suppose the distance between the center of the sphere to that particle is x. Okay, so now I think all of you are familiar with Newton's law of gravitation. Okay, that the gravitational force that acts on this particle, that is given by gmm upon x square, but with a minus sign I cap like this. because it's an attractive force. So this we see comes in which category? It comes in category of central forces which are conservative. So there is some formula for gravitational potential energy, and how that formula comes is that gravitational potential energy is negative of work done by this gravitational force from infinity to that distance x. That is, if I bring this particle from infinity to this, either I'm holding this stationary while I'm doing that, or maybe both of them are at plus minus infinity, but I'm bringing them from that to a distance of x. Whichever be the case, it does not matter. Okay, the distance between the center of this guy and this particle is changing from infinity to x. So in the process, the negative of work done by gravity, which will be equal to positive of work done by external agent, that will be equal to the absolute gravitational potential energy. So when we do that, this comes out to be, so I'm not getting into the details of this, but this comes out to be the potential energy is G minus Gmm divided by x. Okay, now we apply that concept that suppose the height of this particle from the ground is h, and this is radius of the earth. Okay, so I can substitute x over here with r plus x, r plus h. Okay, and then what I can do is I can apply binomial approximation. Okay, r plus h. Okay, so now what I can see is at the ground level, at the surface level, how much is the potential energy? It is minus gm upon r. Okay, and at a height h above the ground, what is the gravitational potential energy? It is minus gmr into, now see, I've taken r common in the denominator, so I'll get 1 plus h by r to the power minus 1. So I'll bring that inside. So it will become what? It will become this plus mgh. When you open this term, it will become this plus mgh. You understanding that? It's how it's, there's also a small m here. Okay, so the change in potential energy is becoming how much? Okay, yeah. It's not? Yeah, so it's not much. No, the thing is like, that's why we are able to say that the difference in potential energy between this and this is equal to m small g into h, where small g is capital Gm upon r square. Okay, but if for example h is large compared to r, like h is half of r or 2/3 or even double of r, then we cannot do this binomial approximation. So then this formula does not apply. Are you understanding the point? Okay, so that's the difference between these two. Okay. So anyway, so we will let this be. Okay, so that's done. Yeah. This is from objective 1. Okay, so let's work out this question. Question number 10. So it says that a uniform sphere is placed on a smooth horizontal surface and a force F is applied to it at a distance h above the surface. The acceleration of the center is how much? Okay. So this is a smooth horizontal surface. This is the side view of a sphere. Okay. Okay, so we are applying a force like this, let's say, where this distance is h from the ground, line of action. So what should be the acceleration of the center of mass? Okay, so through the center of mass there is mg acting. Okay, through this point there's normal reaction n acting. Okay, so this system will accelerate like this. Okay, now because of this force it might start spinning also because it's creating a torque, but we are not asked for that. No? We are just asked to find what is the linear acceleration of the center of mass. So as far as that is concerned, we don't even have to treat this like a system of particles problem. This is a dynamics problem. No? We will, to understand the translational motion, we will treat the center of mass like an equivalent particle and we'll just understand the forces acting on it. And that's it. These are the forces which are acting on it. There's no chance of friction acting because it said it's a, okay. So how much will be the linear acceleration of the center of mass? F by m. That's it. It'll have a horizontal acceleration of F by m. Okay. Achha, now when it's saying that, okay, now we can see that as long as h is between 0 and 2r, is always going to be this. If h is more than 2r, then I'm applying the force into blank space. It's not acting on this. So acceleration becomes 0. So that's the only limitation in this question. Okay. It's not a question of maximum minimum. It is independent of h. Okay. But as long as there's the limitation that h should not exceed 2r. But then that's already said because it said the force is acting on the sphere. No? It's not saying that the force is acting at a distance of h above. And we're not sure whether it's on the sphere or not. Okay. So we'll rule out that part that h is greater than 2. Okay. So this seems a bit unintuitive right now, no? Because it seems to you that, okay, if I apply too much force below, it might tend to topple over and all that. But that is because we are considering in our mind something to do with friction and something to do with slipping. So very soon when we learn about rolling in rotational mechanics in the next chapter, then it will become clear to you what happens if I convert that into a rough surface from a smooth surface. And then I have to consider toppling situation also. Okay. But here what is happening, we have to consider the ground smooth. So what is happening, doesn't matter whether I'm applying the force right through the center, above it or below it. Okay, the only difference that above or below will make is that if I am applying from below, while the body is moving like this, it will also spin like this. So it will have an anti-clockwise spin while it is moving forward. Whereas if I apply it above the center of mass, that is h is between r and 2r, then it will have a clockwise spin as it is moving. But every time the net force on the system is equal to F horizontal. So every time the acceleration of the net center of mass will be the net force divided by the total mass, which will be F prime. So that is independent of H in the frictionless situation, of course, by the way. You know? Okay. Yeah.
I'm still getting the wrong answer for that question.
Okay, I'll check out your solution later. Don't worry, it's a simple thing. Okay. Achha, now any doubts on the module or anything else? Anyone? Okay. So okay, let's maybe do one or two questions. Okay, before we move on to something else. Rotation. So we'll do a couple of revision questions. Okay. So let's do one example question like this. So this is a combination of two inclined planes, which has a sharp corner point over here. Okay. So this angle is 60 degrees. And this angle is 37 degrees. And this height is h. And from a point which is also at a height h from this corner point, we release a particle. Okay. All the surfaces are smooth. Okay. Now, sorry, this is not 37. Let's make a correction. Should be 30 degrees. Okay. So particle so this is the point A. So in the first case, we consider that we release the particle from rest from A, it slides down and it hits this sharp corner point P and makes a perfectly inelastic collision over there. So That means it sticks to that surface, it doesn't bounce off. Okay, so it hits this and then changes direction and goes along that surface and reaches the point B. So we have to find the speed by the time it reaches the point B. Perfectly inelastic. So coefficient of restitution is 0. Okay. So the hint to you is you already know that, for example, if this is a surface on which a particle comes and hits like this, suppose you project it from somewhere and it comes and hits with a velocity v like this. What will happen if the collision is perfectly inelastic? Then immediately after impact, the velocity will become like this. No? It will have only a tangential component. It will not have a normal component. Okay. So if this velocity after impact is vf, okay, and this angle is theta, if this angle is theta, then for E equal to 0 case here, this final velocity, which will be purely tangential, will be equal to v cos theta in this case. Because tangential component of momentum is conserved and separation velocity has become 0. So it does not have any normal component. Okay. Whereas on the other hand, if E had been 1, it would have gone like this. So it would have gone at the same theta with the same magnitude of speed. Got it now? So that concept now you have to apply. The only thing is now you have to think in terms of twisted axis. Which is the surface at which it is hitting? It's hitting this surface, no? So that's beyond P. So it's hitting a surface along this line. And when it impacts that surface, how is it moving? It's moving along this line. No? So particle moving along this surface goes and impacts another surface which is here. So that's why you have to work out the. Yes. So what will happen? Normal component will be 0. Separation velocity will be 0. Okay. But the tangential component will remain conserved. So when it's coming and hitting at this corner point, it's hitting with a velocity vector which is like this. So that velocity vector has a normal component that gets absorbed by the moment impulse, but it has a tangential component and nothing happens to that tangential component. That remains conserved. Whereas also we'll do a B part of this question where we'll understand that instead if the collision is perfectly elastic, then what kind of range it would have, because then it would bounce off the surface. Okay, Siddharth, just try to work it out numerically also. I'll check your answer. I think you have given the velocity just after impact at the point P. Oh no, it's correct. Yeah. Just work it out numerically also. Okay, so just before impact, what is the speed of this particle when it is about to hit that point P? So first of all, that velocity will be along this line. So again, that's a little difficult to draw here. So this will be like the impact velocity, na, V naught. Okay, so we need to do two things. We need to understand how much that V naught is in magnitude and also what angle it is making. So can you tell me what angle that is making? So that's where geometry comes in. See, if you just continue this surface, the lower surface, this is the tangent, no, to the surface. Okay, so this is at how much angle over here? This is at 30 degrees. So this angle is also 30 degrees. Okay, so therefore this angle here is how much? It is 30 degrees. So the tangential component of this V naught is the cos 30 component, and the normal component is the sin 30 component. You understand? So it's like, if you just think of it independently now, you have this surface, okay, and at this point P, you have a particle which is coming in and hitting it with a velocity which is like this, where this angle is 30 degrees. This is what is happening. Okay? It's coming along this plane and hitting it, but with a velocity V naught, which is making what angle with that surface? It's making an angle of 30. You understanding, no? So it's a matter of simple geometry. If you have one surface which is at alpha and another surface which is at beta, then between these two surfaces, what is this angle? It is alpha. It is beta minus alpha. So that's what's happening here. 60 and 30. So the angle between the two surfaces is 30. Got it? Understood? Okay. So V naught is how much? It is root 2 GH. Just apply work energy. There's no friction. So that's 20 meters per second. Okay. So on impact, what is the tangential component? It is V naught cos 30. So it is 10 root 3. So this will remain conserved. Okay. And what is the normal component? That is our sin 30 component. But that is our approach velocity actually. And that is V naught sin 30. So that is 10 meters per second. Here. So immediately after impact, what we'll see that this particle is going along this surface, but with a speed of how much? 10 root 3. Its kinetic energy is drastically reduced from half mv naught square to half mv naught cos 30 whole square. Okay, and then again we'll apply work energy from just after impact to B. We can't apply work energy from A to B because in between there's an event where there's dissipation of energy. But from A till the impact happens, there's one round of conservation of kinetic energy. Conservation of mechanical energy, and then after impact till it hits the point B, there's another. Sorry, we can. That's the velocity you're getting. Okay, I'll just check the answer. 10 root 7. Yeah, I think that's correct. Okay, now if you finish that part, then solve the next part where instead of this being a perfectly inelastic collision, now it's making a perfectly elastic collision. So it will bounce at that point. So to find the range for the first bounce. Okay, instead if it makes an elastic collision, then it will bounce off from the point P and again hit the surface at some other point. So to find that range of the projectile motion from the point P to there. Okay, so I'll just verify the answer and complete the calculation for others also. Okay. You can do that also. It has an acceleration of g sine, but the displacement will become h by sine. So you know that sine factor cancels out. Okay. So first of all, what we can see now here is that immediately after the impact is over, the particle has a tangential velocity. This was 10 root 3. So now by the time it reaches here, it has a velocity of VB. That's where we. So because E is equal to 0, so separation velocity would have been 0. So the normal component is equal to 0 after impact, whereas the tangential component remains V naught, sorry, cos. This is coming from conservation of tangential component of momentum. In an oblique impact. So now so 10 root 7 is in fact the correct answer for this part. Okay. Now the next part we'll do. We'll assume that the particle comes sliding down and then makes an elastic impact. So it goes into a projectile motion. Yeah. So got the range, anyone? Okay, so just before impact, we've already seen that it's having a velocity which is like this. Along this line. Okay. So V naught was 20 meters per second, right? And theta was 30 degrees just before impact. Okay. Root 2 GH V naught. Okay. So now if the collision is perfectly elastic, 10 root 3 was the tangential component. No? I'm saying just before impact. Okay. So now if the collision is perfectly elastic, then what will happen? It will have a velocity V like this at an angle, let's say phi like this. Okay. Where we know that basically V will be equal to V naught. Yes, come in. And phi will be equal to theta when we take the case of E is equal to 1. No, you can write that directly. We don't need to solve that. Okay. But the way to solve it, because basically V cos phi will be equal to V naught cos theta. Okay. This is the tangential component of momentum conserved. Okay. And V sin phi should be E times V naught sin theta. Here you see theta and sin and cos are interchanged because the angle is not with respect to the normal. The angle is with respect to the tangent to the surface. Okay. So this is the general equation, conservation of tangential momentum. And this is the concept of E, that separation upon approach velocity. So this all we know. Okay. So we also know that this, when we take E equal to 0, we get this special case. So now we have to just solve the projectile motion from here to here. So for that, what we'll do is we'll just take this as our x-axis. We'll take the normal as our y-axis. Okay. So we have, if we take this instant of time as t equal to 0 and this instant of time when it hits as t equal to capital T. So to find the range, so in general, we'll have what x is equal to v cos theta t, so rather v cos phi plus half, ये कितना हो जाएगा g, this x component g will be how much? It will be g sin 30. Okay. So when we substitute these values and all, so we can see that v is equal to 10 root 3 and phi is equal to 30. So what we'll get here, we get 10 root 3 into root 3 by 2. So that will be 5t. Okay. And this will be plus 5 by 2t square. This is x as a function of time. Taking g as 10 and sin 30 is half. Okay. And similarly, y as a function of time will become what? Y will become v sin phi. By 15, 10 root 3, into root 3 by 2. So yes, into 3. So 15t, correct. This will be 15t. 15t, yeah. Yeah, and minus half g cos 30 t square. So this will become how much now? Oh, wait. Not 10 root 3. V naught is, my mistake. Yeah. This is 10 only. Because this time it's conserved now. You understanding? This time it's not the tangential component. V is conserved now. Kinetic energy is conserved. So V is 20 only. Okay. So what is this term now? 20 cos 30. So that's 10 root 3. Yeah. So this term is 10 root 3. Okay. And this term is going to be how much? 10t. Minus 5 root 3 by 2, right? This is y as a function of time. Okay. So then we substitute y coordinate as 0. So we'll get the time of flight, substitute the time in the first equation. So we'll get the range. So time is coming how much? 2 by root 3, is it? Or 4 by root 3? Okay. So put 4 by root 3 here. So y is equal to 0 at t equal to capital T. So you will get and then x is equal to r at t equal to capital T. So r will become 10 root 3 into 4 by root 3. So that's how much? 40 plus 5 by 3 into 16 by, sorry, 5 by 2 into 16 by 3, right? So that's how much? 5 into 16. So that's 80 divided by 6, is it? 5 by 2 into 16 by 3, yeah. Okay, so that's 40 by 3. So that's becoming how much now? So 40 plus 13.33. No, so that's 53.33. Why 9, beta? No, it's root 3 ka square, na beta? The time is 4 by root 3, na? Okay. So this is the final answer we should be getting for the range. Yeah. Okay, so this was our revision question of the day for system of particles. Okay, now we will move on to an introduction into rotational mechanics. So many different names for this section of physics, including rotational dynamics, rotational mechanics, rigid body mechanics, rigid body dynamics, etc. So in this we study basically complete rigid body motion. Okay. That is kinematics as well as dynamics of a rigid body in general motion. And by general motion, what we mean to say is it is a combination of rotation and translation. So basically, any rigid body that is moving like this. Its center of mass has some velocity, and at the same time, about the center of mass, there is some spin also. That's that. So we are talking about a rigid body that's going in this type of motion. Okay. So it's combination of rotation as well as translation. So that is the whole purpose. Rigid body motion, the most complicated case of this is this. Okay. But of course, a special case of this is if the translation is zero, so there's only rotation happening. Then we call it pure rotation. And the motion of this fan above you or the motion of this pendulum, these are all examples of pure rotation because they're rotation about a fixed axis. Or if we remove the rotation and only translation is happening, that's what we've seen in particle dynamics before, like an object sliding down an inclined plane or anything like that. Okay. So now we will learn how to combine all these concepts and discuss both the equations of motion as well as the equations of dynamics. Okay, for this general type of motion. So we'll start with the most basic thing in this, that we all know the definition of rigid body, so I'm not getting into that. A rigid body is a collection of particles which are rigidly attached to each other. So it has a fixed shape and size, and obviously fixed density, volume, mass, and all that. So ultimately, a rigid body is a system of particles like we've seen before, but it's a system of particles where the particles are all rigidly attached to each other. That means with respect to each other, their distance cannot change and their position cannot change. Okay. So having understood that, now we have seen translation of a rigid body before. So now we'll come to the next simplest type of motion, which is pure rotation of a rigid body. Oh, I managed to skip some pages. All right. Now, so let's go to this. Okay. So we have already seen what is the meaning of pure translation of rigid body. So that is when the motion is such that the body itself can be treated like an equivalent particle located at its center of mass. Okay. So basically, when a body is moving in such a way that after some time, let's say the same body is reached from here to here. So during this time, only this has happened. So as the center of mass is reached from here to here, any other particle in the rigid body, which let's say is over here, that particle will also be having the same velocity, same displacement, same everything. Okay, so any particle P has a velocity such that it is equal to the velocity of the center of mass at any instant. So all particles have their identical motion. So that is called pure translation. Okay, so any particle at any point of time, at any instant, has an instantaneous velocity equal to the velocity of the center of mass. So that means there is pure translation. Okay. And for pure translation, we have all these equations that net force is equal to mass into acceleration of center of mass. Work done by external forces plus work done by non-conservative force is change in kinetic energy plus change in potential energy, where we define kinetic energy as half mv/cm square. So all this applies to pure translation. Okay, so if this entire rigid body of mass m is in pure translation, which means that any point in it at any instant of time has identical velocity vector as the center of mass, then we can treat its kinetic energy as pure translational kinetic energy, and that is given by the formula half mv/cm square. Okay. So this is in fact now from now on we will call this term as pure translational kinetic energy. Okay, so that is pure translational kinetic energy. But as we have already learned in certain parts of center of mass, this may not always be the case, right? Like you have two blocks attached to a spring, which is a non-rigid body then, because the spring is elastic in nature. Then the velocity of the center of mass at any instant is not equal to either of the block's velocity. And therefore, we cannot write the total kinetic energy of the system as half of m1 plus m2 into vcm square. That equation is not correct. It's half m1 v1 square plus half m2 v2 square. Okay, so then again, that is an example of a non-rigid body which is in non-translational motion. It's in different type of motion. Okay. But now we talk about rigid body which is in non-translational motion. That means the bodies, I mean the particles within my system, they are rigidly attached. But at the same time, this equation is not true, that the velocity of any particle at any instant is not necessarily equal to the velocity of the center of mass. And that you can understand happens in general rigid body motion. Okay. So for example, if we see a rod which is moving like this, such that while the center of mass is going like this, but it is also spinning like this about the center of mass. It has some instantaneous angular speed. Now, logically, we'll understand that next moment the rod would have reached somewhere like this. Now, it would have gone like this. So you can see that this particle has had a forward velocity. This particle has in fact had a backward velocity. So where the center of mass and all the particles are having identical motion, they're not having identical motion. So when that happens, we cannot say that the motion is pure translation anymore. In fact, in this case, it is a combination of rotation and translation, because the center of mass is translating, and while that is happening about the center of mass, there is some rotation. Now, before we come to that general type of most complicated type of motion, we'll come to, so this you can say is the simplest way in which a rigid body is moving, which is pure translation. Now, next simplest way is what? Pure rotation. So that is when translation is not happening, but rotation is happening. So if you think about classifying the different types of motion, pure translation is the simplest. Now the next simplest type of motion is pure rotation of a rigid body. Now this is what is going to be new for us here today, but this will not be difficult to understand because we've already seen pure rotation of a single particle, and that was circular motion. Now the only difference is a rigid body is a collection of many particles, and pure rotation means all of them are doing circular motion together about a common fixed axis. Okay. So pure rotation is the type of motion of a rigid body. So obviously we're talking about at a later stage. Okay, right now it is only about rigid body motion, because that rigid body could be influenced by a spring. You understanding? But we will not consider body consisting of the spring as part of it. The spring will become an external agent in our systems. Okay. Yeah, so we are talking about pure rotation of a rigid body. So that is defined as rotation about a fixed axis. Okay. Now, the moment I use a term like fixed axis, you understand anything to do with kinematics is always whatever statement I make, it is dependent on my reference frame. No? So if I'm saying right now this fan has a fixed axis, that's with respect to my reference frame. Somebody standing on the moon, with respect to them, the axis is changing. Or even somebody sitting in a bus outside, with respect to them, this fan doesn't have a fixed axis anymore. So I can say the pure rotation is in a particular frame where in that frame the axis is fixed. Then we say that, okay, in that frame the motion is pure rotation. So how do we describe this motion? So if a rigid body is moving about, let's say, now I'll represent this axis with a dot, which shows that the axis is coming out of the plane. Okay. So if it's rotating about that fixed axis, then every particle that is part of the rigid body is describing concentric circular motion, but about a common fixed axis. And while the individual velocities of the particles will be different, the individual displacements will be different, therefore accelerations will be different, but the angular parameters for the circular motion will all be the same. By the time the center of mass has gone through 90-degree angular displacement, the corner point has also gone through 90 degrees. This one is, so they will have all common angular parameters, that is delta, theta, omega, and alpha. The angular parameters will be common for all of them because they're all rotating as part of a rigid body about a common fixed axis. So that becomes the most important property, that the moment the axis is fixed, that means every constituent particle Okay, so angular velocity and angular acceleration treated like vector quantities now. So here you can see, if you consider the center of mass, let's say somewhere here, at this given instant, it will have a velocity like this. Okay, if you consider some other particle, so this particle P over here, at this instant, it has some different velocity. Not only different in magnitude, but different in direction also. But P and the center of mass will have common value of omega, alpha, and delta theta. After some time, if this is rotated by 30 degrees, the center of mass has also covered angular displacement of 30. P has also covered angular displacement of 30. And whatever is the omega in radians per second, they're having common value of omega. If they're having alpha, then they're having common value of alpha. Right? Then magnitude is same, but direction is not same. So in general, I'm saying different particles are having different values of velocity. Remember velocity. Okay. So you can see velocity of the particle P is not equal to velocity of the center of mass. Okay, but omega and alpha are same for both. Okay, so that is the property of the this thing, pure rotation of a rigid body. The angular motion is happening simultaneously for all of them at a common value of. Okay. Even displacement will not be same. No? After some time, the center of mass is reached here, let's say. So by then, this particle has reached here. So the displacement of the center of mass is like this. The displacement of that particle is something else. May be same in magnitude, but may not be same in direction at least. Right? This is clear? Okay, so now having understood this basic definition of pure rotation, now we'll come to the first important new parameter for us. Okay, and through that we will learn of a concept called moment of inertia or rotational inertia, which you might have heard about before. Okay, how we define it. Okay. So we are jumping a little bit, instead of first describing kinematics, okay, which we'll come back to, we are getting into kinetic energy. Okay, so the first property of, or the first formula that I'm going to discuss about rigid body in pure rotation is going to be how to express the kinetic energy of that rigid body. Because definitely we cannot express it as half mvcm square, because it's not translation. No? That only applies in the case of translation. So how to describe the kinetic energy of a rigid body in pure rotation? And through this only we will learn, or we'll have our first encounter of the quantity called moment of inertia. Okay. So this is our fixed axis about which the rotation is happening. Let's say it's coming out of the plane like this. Okay. Now consider any arbitrary particle, small particle of mass dm, which is at the position vector r with respect to the axis of rotation. And what we mean by position vector r means its perpendicular distance. Like imagine this is three-dimensional, so this is a rigid body like this. So a particle might be somewhere here, outside the frame of the board. So we are not putting the r vector as this point joining that. We are dropping a perpendicular from the axis of rotation. Understood now? So then that r vector becomes the radius of its circular path. No? So for a particle of mass dm at position vector r with respect to the radius, with respect to the axis of rotation, not with respect to any particular point, but with respect to the axis of rotation. Okay. What is the instantaneous velocity? So its speed is r omega, correct? Okay, remember in circular motion we had seen this cross product definition also. Here if it is anti-clockwise, then omega is coming out of the plane. So omega cross r will be what? Point your thumb along omega and your fingers along r. So where omega cross r is pointing like this. So this is the instantaneous velocity of the particle. Its direction is perpendicular to r and omega, Okay, and its magnitude is how much? R omega. Okay, so imagine this is a like a potato shaped body, and this is your axis of rotation, like Z axis coming out of the plane. X and Y axis are over here. So any particle could be sitting at any X, Y, Z. No? So R vector is what? It is the perpendicular drop from this onto that. Understood? No? So it will not have a Z component. It will be just X I cap plus Y J cap. Like that. Okay. So in that case, when we have taken R as the position of that particle, not with respect to this point, but with respect to this whole axis. So that's the difference between the reference of a point with respect to another point or with respect to an axis. If I say that, okay, this point is the origin and I have a point X, Y, Z over here, what is the position vector with respect to the origin? It is X I cap plus Y J cap plus Z K cap. But if I say that this axis is my Z axis and a point is sitting anywhere over here at X, Y, Z, then what is its position with respect to the Z axis? Then it is only X I cap plus Y J cap. So it is a perpendicular drop from the Z axis onto that particle. So that one. So if the whole body is rotating about the Z axis, that particle is in circular motion with that radius vector R. No? Okay, so what will its instantaneous velocity be? Omega cross R. So its speed will be R omega in magnitude. So what about the particle's kinetic energy? Is this? So it is half dm into R square omega square. Okay. So now how will we express the kinetic energy of the entire rigid body? We have to just integrate that kinetic energy for all the particles. So the total kinetic energy of that rigid body will come by integrating this over all the particles. Now next, when we integrate, you can see we are going to integrate this term. So for each particle dm, R has a different value, but omega is common. So half omega square will come outside. So we'll be left with some quantity which is like an integrated term into half of omega square. So that is how we'll express the kinetic energy. And we'll see just like translational kinetic energy is proportional to V square, but the factor is half mv square. Like that, rotational kinetic energy is proportional to omega square, but the term is something else into half. And that something else is that integration of R square dm, which becomes another property of the body. Instead of just the pure inertia, which is mass, it becomes the rotational inertia. It becomes about how the mass is distributed with respect to the axis of rotation. So that is called moment of inertia. Okay, so we're coming to that. Just note down up to this step first. So up to this step, I think it's pretty simple, right? If you just look at any particular particle with respect to the axis of rotation, just think in terms of scalars only. If you drop a perpendicular, it's at a distance of small r. The magnitude of r, it's at a distance of small r. So its instantaneous speed is how much? It's r omega. So its instantaneous kinetic energy is how much? This much. Okay, but now we have to remove our perspective from instead of just that single particle, we are looking at that whole collection of particles moving together. So together, how much kinetic energy they'll possess? The sum of all of them. So that summation will have to be done by integration because there are infinite number of particles of differential mass dm. So that summation has to be done by integration. So that's why integration comes in. And once integration comes in, you see when you are integrating, omega is a term which is common to all the dm's. So omega square and half will come outside of the integration. So again, we have kinetic energy is proportional to omega square into half into some other factor instead of mass. And that other factor becomes the inertia of the body with respect to rotation. Whereas mass was the inertia of the body with respect to translation, because translational kinetic energy was what? Half mv square.
Mass would be inertia of the body with respect to transition.
That's why we also call mass as the translational inertia. That's why we define linear translational momentum as m into v. We define translational kinetic energy as what? Half mv square, right? Whereas when we come to rotation, all those equations change. We define angular momentum as I into omega, where I is moment of inertia and omega is angular velocity. We define rotational kinetic energy as half I omega square, where I is again rotational inertia and omega is the angular speed. So your translational terms convert into rotational terms. So just like V converts to omega, acceleration converts to alpha. Linear displacement converts to delta theta, angular displacement. Like that, mass converts to something else, and that is called moment of inertia. I'll explain. You can understand that physically also.
Sir, I have a doubt that how did you get magnitude of V as R omega, and I didn't get how did you get that direction?
Just a moment, Beta. Again, please.
Sir, I didn't get how you got magnitude of V as R omega, and it's
how we got the magnitude of V as R omega. Circular motion, Beta. So see over here, in circular motion, we define the velocity of a particle as omega cross R. How that definition had come, you remember? Going back to circular motion, we define R as what? Magnitude of the radius into cos theta I cap plus sin theta j cap. Then we differentiate that. Are you remembering now, Dhruv?
Yes, sir. Yes, sir.
In circular motion, if you define the instantaneous position as something like that, no? Going back to circular motion. Okay. If at some particular instant the position vector was r, then we saw that the velocity vector automatically becomes like this, because you have that r is so it is like this, because r cap is this unit vector. Then velocity comes by differentiating this. So when we differentiate this, it so happens that we get r omega into minus sin theta I cap plus cos theta j cap. So we get the relation that velocity is r omega theta cap, which we express as a cross product sometimes, and that becomes omega cross r. Okay. So all this is coming from the background of circular motion. So again, the mod of this equation is what? The mod of this equation is this one, that V is equal to R omega. Okay. So now coming back to the total kinetic energy of the rigid body. Okay. In pure rotation, that is, that will become integration of the kinetic energy of each of these particles. Like this. Okay. Okay. So this is integrated over the entire mass of the rigid body. Okay. So this quantity is given a special name, moment of inertia, because it has, we'll discuss a lot in detail about this. If you understand, it is a quantity which depends not only on the mass of the body, but it depends on the distribution of the mass. Okay. So the quantity I is called moment of inertia. Okay. It has dimensions of ml square. Okay. So what happened here now? And it is a physical property, okay, defined by the distribution of the body's mass with respect to the axis of rotation. Okay. So how large the rotational inertia is numerically in kg meter square not only depends on how large the mass is, but how further away the mass is from the axis of rotation. Okay. Which is why, for example, this door, okay, it has a certain resistance to rotation, right? To change its angular momentum or to change its rotational kinetic energy, you have to do a certain amount of work on it. Okay. Now suppose we attach a very heavy block to it. It will appear to be heavier, But now take two scenarios. One, I'm attaching the block here. And in the second situation, I'm attaching the block right over here near the edge of the door, in which case it will appear to be even heavier. When I attach the block near the edge, further away from the axis. So if I'm adding mass to this already rigid body, where I should add it so that the added mass will contribute maximum to inertia and make the door appear heavier, I should attach it further away from the axis. Why? Because the contribution of mass is with what? M into R square. So the larger the value of R, the more the moment of inertia is becoming. Okay, so that's one simple physical way to understand why inertia of a body with respect to rotation doesn't only depend on the total mass of the body, but it depends on where the mass is with respect to the axis of rotation. Yes.
So how did you know that this quantity is the inertia of the body?
That's a definition. See, we are seeing that this is something which is independent of omega. No? It's a physical property of the body independent of the motion. So we are just defining that as a new quantity I, where by definition that quantity I is what? R squared dm. Now when we observe that quantity, how we calculate it? It has to do with distribution of the particles with respect to the axis. No? Because R is the distance. So we understand that what kind of physical property it is. It's a distribution based physical property. It's a physical property which depends on how the mass of the body is distributed with respect to the axis of rotation. Okay, so this is more of a definition. Okay, so now we can draw an analogy that in the case of pure translation, okay, we define the kinetic energy as half m into v square, no? Where v was translational velocity and m was the inertia. We didn't talk about it as translational inertia because at that stage we were talking only about translation. But now when we talk about pure rotation, when we talk about pure rotation, the kinetic energy formula, it changes to, so there's a symmetry in the terms. You can see V has changed to omega, but likewise M has also changed to something else. And it has changed to something which is again a property of that body. But that property of the body does not have to do with only mass. It also has to do with how the mass is located with respect to the axis of rotation, how far away it is located or how near it is located. So that property is now called moment of inertia, or it is also called rotational inertia. Another name for this is also rotational inertia, but commonly we use the name moment of inertia. Okay.
So the way the mass of the body influences motion.
Yes, the distribution of the mass influences its motion. Whether it appears to be heavier or lighter, whether it appears to be having more inertia or less inertia, it depends on the total mass of the body, but as well as how the mass is distributed. One body having more mass compared to another is likely to appear heavier, but in a strange situation, it might appear to be lighter also if the distance is very far from the axis of rotation. Okay. So this is our first instance of the quantity moment of inertia, and we will keep coming across many instances of this quantity, not only in terms of when we compare the relation of kinetic energy. By the way, this is now called kinetic energy of pure rotation or rotational kinetic energy, and this is called translational kinetic energy. Okay, so later we'll see when the body is in a combination of rotation and translation, then the net kinetic energy is the sum of the two. It is the translational kinetic energy because of the velocity of the center of mass, plus the rotational kinetic energy because of the rotation about the center of mass. But okay, right now we are describing it only in terms of a rigid body in pure rotation about a fixed axis. So we will see that this kind of analogy will work out not only when we are defining kinetic energy, but for example, when we are defining dynamics. For translation, we say net external force is equal to mass into acceleration. Here it will become something called net torque, which has to do with moment of force, and that will be equal to I into alpha. So mass will be replaced with I, and acceleration will be replaced with angular acceleration. Okay. Okay, can I rub this on this clear? Okay. I mean, can I move on to the next page? Good. So let's talk a little bit more about moment of inertia. So for example, if we have a thin uniform rod, okay, in rotation about an axis which is its perpendicular bisector, okay, then what about its moment of inertia? So thin uniform rod of mass m and length l. Okay, so this किसका? नहीं मेरे पास नहीं चाहिए, मेरे को आइडिया नहीं, मैम के पास होगा नीचे, IITians वो जो आपको पता है ना काउंसलिंग रूम में नीचे जो है ना मैडम, उनके पास होना चाहिए. Okay, so suppose we have, doesn't exactly look like a thin rod. Let's see if I can do better than that. Okay, so we have a thin uniform rod, and now let's say we have fixed it about a hinge or something, okay, so that it's going to rotate about this axis like this. So it's going to spin like this, okay, about an axis passing through its center. So it's a perpendicular bisector. So given that the mass of the rod is m and the length is l, how much should be the moment of inertia? Because then we will also know that once we know the moment of inertia, we can calculate how much the kinetic energy is for this. Given its angular speed omega, it will be half I into omega square. But we have to know how to calculate I, and how that will come. That will come from this concept of I, that it has to do with, we are summing up for all the particles the quantity m into r square. But we are summing up by using what? Integration. So the technique of integration used will be the same that you've seen in center of mass. That is, if it's a linear distribution, then dm is lambda dl. So we have to cut length elements. If it's a surface distribution, then we have to cut surface elements. So it's sigma dn. If it's a volume, like that. Okay. So the same techniques, and not only that, like the same types of elements we had seen, we'll see repeated here. Like if it's a linear rod, then we'll just slice it into d axis, and we take this as our x-axis. Whereas had it been a ring, then we would have taken r d theta as the dl. Right. So those methods that we've learned earlier in center of mass, they're going to be equally useful here also. Okay. So let's see how this will work out. So what we'll do is, we'll say at some position x with respect to this axis, taking this as the origin of our x-axis, we'll slice a thin section of thickness dx. Okay. So for this element, so this, what we can call as the differential length element. Okay. So it has a differential length, which we have written over here as dx, and therefore it will have a differential mass. So we'll replace lambda with m by l. So we'll replace its mass as this. Okay. And what about its distance from the axis of rotation? Is nothing but x. Okay. So our r will become how much? Our r will become x. Okay. So moment of inertia, which is integration r square dm, will become integration x square m by l dx. Now just tell me what should be the limits for this integration. The whole length is l. Okay. So my x coordinate will go from this end where it's minus l by 2 to that end where it's plus l by 2. Okay. So if this is a and this is b, so this will be integrated from the point a so from minus l by 2 to plus l by 2, we have to do this integration. Okay, so the logic of the limits is clear now, because this axis is passing through the midpoint. So the x coordinate of the point A will be minus L by 2 and 2 plus L by 2. So how much are we getting on doing this integration? Yes, very good. And that is our first standard formula that we have to memorize for moment of inertia. For standard type of rigid bodies, we'll remember the formula of moment of inertia, just like we had done a few formulae of center of mass. Okay, so that becomes part of this chapter. So this is our first official formula today, that moment of inertia of a thin uniform rod. But remember, that is only when the axis is the perpendicular bisector. If I change the axis position, moment of inertia will change. The same rigid body will have a different moment of inertia because the axis has changed. So the distribution of mass has changed, even though the total mass is the same. Okay, so this will become m, okay, into x cube by, sorry, m by L, yeah, into x cube by 3, right? Because we have x squared dx integration. The limits are from minus L by 2 to plus L by 2. Okay. I'll just show the step earlier. So when I'm doing this, okay. So on substituting the limits and all, we get the standard formula ml square by 12. It means that this is, so for example, if I'm comparing two rods of the same mass but of different lengths, how heavy they will appear to be to make it rotate about that axis. That comparison is the moment of inertia. Or if both of them are rotating with the same omega, the ratio of the kinetic energies will be I1 is to I2. Okay, so the same role that mass plays in the case of translation, now that role is played by moment of inertia in the case of rotation. Is a mass distribution with respect to the axis of rotation. So that plays the role of inertia. What is inertia? The ability of the body to change its state of uniform motion. So suppose this is already rotating at some constant omega. Now we have to put some effort to bring it to rest. Now how much effort we have to put in? Now what that effort means right now I have not defined. Later we'll see we have to apply some torque over a period of time. But let's just say, like we're talking logically in terms of how much effort is required to bring it to rest. So if it was translating, it would depend on the linear momentum. No? The more the velocity and the more the mass, the more amount of impulse we have to apply to bring it to rest. Similarly, if it is rotating, it depends on something called angular momentum. So that's I omega. Or if we are thinking in terms of work energy, how much kinetic energy you have to absorb to bring it to rest. So that is half I omega squared. So what that depends on? That depends on two things. It depends on the speed of rotation, which is omega, and it depends on another property, which is the internal property of the body. It's a physical property of the body. And that is basically what? The distribution of mass with respect to its axis, which is moment of inertia. That is defined by this integration r squared. Yeah, of course. Because as I said, like today we have seen it only in context of kinetic energy, half I omega square. Later we'll see it in context of dynamics and then momentum conservation. So you'll get more idea about this. Okay, but through this itself you are getting some idea of it, no?
So this is sort of an analogy of weight of an object in motion.
Not weight, because weight has to do with gravity, remember. It's an analogy between mass in translation and rotational inertia in rotation. Yes. Just remember the analogy this way, that as of now, how we have understood the analogy, not like that, of course. As of now, how we have understood the kind of analogy, that if we are putting a body of mass m into translation with a speed v, how much energy we have to give? Half mv square. But similarly, if we are taking a body like this and setting it into rotation about a fixed axis, how much energy we have to give? Half I omega square. So there is the comparison. For translation, the energy we are giving to develop that much kinetic energy is directly proportional to mass and into square of the linear speed. So like that, in the case of rotation, the amount of energy we have to convert into kinetic energy is directly proportional to this term, moment of inertia, and directly proportional to omega square, where omega is the angular speed. So that is the analogy over here. So between these two, pure translation and pure rotation, you can see that just like V and omega have an analogy. V is to do with velocity in linear motion. So omega is to do with angular velocity in angular motion. So like that, M is the inertia property in translational motion, whereas I is the property of inertia in rotational motion. So that is the analogy. Yes. We're already learning in one way. You see how I influences the kinetic energy. No, already we have understood one thing. No? So now, for example, if I told you that this rod has a mass of 5 kg and a length of 1 meter, so to bring it to an angular speed of, let's say, 2 pi radians per second, how much work has to be done? So you already understood the application of this half I omega square. Okay, so when I'm working that kinetic energy, is mass alone useful to me? No. Is omega alone useful? Is V of any use? No, not at all, because VCM is 0 over here. So which factors determine the kinetic energy? It is these angular parameters. Omega determines, and similarly, what is the angular equivalent of mass? For the angular motion or for the rotational motion, mass has to be replaced with what? It has to be replaced with another property, which is moment of inertia. Yes. Yes, which different shapes of objects also, and not only different shapes of objects. Then one more example we'll end up with today, just 2 minutes, is that the same rod, if it has a different way of rotating. Okay. Now, one example which is not so direct, okay, is now let's say the axis of rotation is passing through the center of the rod, but it's not perpendicular bisector. It's like this, let's say. So the rod is rotating like this, right, about an axis passing through the center. So let's see, the axis is in this case through the center of mass, but at some angle alpha with respect to the rod. So only when alpha is pi by 2, then it's a perpendicular bisector. Okay, so let's imagine that situation. So let's imagine now that our axis of rotation is like this. It's passing through the center. Okay. So as the rod is rotating, you can see that any particle is describing a circular path like this. Okay, so the rod will define like a inverted or like a double cone shape like that. So now what will be the moment of inertia? Okay. Mass m and length L, what will be the moment of inertia? So what will change is just the value of r for a particular particle. If this is our axis of rotation, alpha is not angular acceleration or anything. Alpha is this angle, or just think of it as beta so that you don't confuse with angular acceleration. It's making some angle beta. Suppose we have that case. So this angle is beta. Okay. So now again, what we'll do is we will take, when we are doing the calculation, we'll still take x as the distance from here. We'll take this as dx. But now what about r? R will not be this. R will be this. Okay. So this also explains to you the importance of the quantity r in the case of moment of inertia. It is the position of a particle with respect to the axis of rotation. That means from the axis of rotation, the perpendicular distance at which the particle lies. So as this body is going in omega like this particular particle is describing a circle with what radius? R. No? So its instantaneous speed will be r omega. So its kinetic energy will be how much? Half dm into r square omega square. So the whole thing's kinetic energy, half I omega square. So how we'll calculate I? By again integration r squared dm. What else we'll consider? Tell? How then? Because the mass is distributed over this axis. No? The mass is not distributed over this axis. Understanding? This r is just the distance, but the actual distribution of mass is happening over what? The length of the rod. No? So we have to consider that way. Okay. So dm here is again m by l dx. Okay. But what about r now? R now you can see depends on this angle. It is x
sine beta.
Sine beta, yes, correct. So when we do the integration, there will be a sine square beta term, which will come out. So it will just become ml square by 12 into sine square beta, in which if you put beta as 90 degrees, then it reduces to that same formula. But also if you put beta as 0, it comes to 0. Why? Because then your rod is like this. So if your rod is rotating like this about its own axis, it's hardly got any kinetic energy. It's not got any moment of inertia. So all the particles are at the axis, so where they are moving about. Okay. So we can define so. No, not like a circle, but what it behaves like is a collection of particles that are spread out over a circle. Yes, yes, correct. That's correct. It behaves like an equivalent rod, which is of length L sine beta instead of beta. Yes, so it's like the projection of this length on this plane, which is perpendicular to. Okay. So anyway, when we substitute this over here, you'll see you'll get that. So we'll get the moment of inertia as m by L square, but now sine square beta also comes out. Sorry, m by L. Okay. Sine square beta also comes out, and x squared dx from minus L by 2 to L by 2. So it will give you ml square by 12 into sine square beta. So very good. One thing you can also see, it's like this, that it's like a m into effective length square by 12. Where that effective length is how much? It is L sine beta. So that is like, you know, when you see this rotating, if you throw light from top, it will project the shadow of a disk. So that disk radius will be how much? L sine beta. So it's acting like that. Okay. So two important concepts we've learned about pure rotation of a rigid body today. One is that when a rigid body is in rotation about a fixed axis, then individual velocities, accelerations, and displacements of particles are not equal. They're different. But the angular parameters are all equal. So they're all doing simultaneous circular motion with common value of omega, common value of alpha, and common value of delta theta. So the angular parameters are common. And then we've seen how to define the rotational kinetic energy of such a body. It is given by a new term called half I omega square, where I is a new physical property we are learning about, which is integration r square dm. So that physical property has dimension of mass into length square, but it is a quantity which depends on the distribution of mass with respect to the axis of rotation. So the further that, so you can see here, if I take beta like 45 or something, I'll get a smaller value of moment of inertia compared to the first case where beta was 90. Why? Because the mass is less away from the axis. Whereas when beta was 90, the mass was furthest away from the axis as possible for this situation. Whereas when I put beta equal to 0, the mass is not away only, it's at the axis. So it does not have any moment of inertia. So if I put beta equal to 0, the rod is like this. So it's just spinning about its own axis. Now it's a thin rod. You're not considering any thickness. So its moment of inertia should be 0 because none of the particles are then moving. They're just at the axis. Okay, so that explains the two extreme cases also. Beta equal to 0. Why the moment of inertia should be 0? Because all the particles are at r equal to 0. They are located at the axis. So there is no distribution. Now, whereas for this kind of axis, when will be the moment of inertia maximum? When beta is 90. Because that's when you place the particles furthest away possible from this axis. Okay. Of course, if you change the axis, then that changes. Okay, a rod could rotate about an axis outside of it also. It could be rotating like this. Okay, I could attach that rod to another thinner rod, okay, massless rod, and make that rotate about this axis. So then that mass is as far away as I like. I can make it 1 kilometer far away. It will have a huge amount of moment of inertia. But in this case, where the axis is passing through the center, the maximum will be when beta is 90. So it's the perpendicular bisector. Minimum will be 0 when beta is 0. So the axis coincides with the rod. So R is 0 for all the particles. Okay, so basic idea of moment of inertia is clear with this. Okay, so we'll conclude today's session here. Next lecture is going to be very important because we are going to look at kinematics of rotational mechanics, and from that we'll get into the concept of torque. So what is torque due to a force and how torque is related to angular acceleration through moment of inertia. So it's from that point onwards you will have to pay a lot of attention to rotational mechanics. So try and complete maximum problems of center of mass by then. Okay, that's it for today's session. People, wish you all the best. Okay. I think
Thank you, sir.